Welcome back. This is Professor Hill, and this is part 1 of the geology section of oceanography. We need to understand a little bit of the basics of how the world works to understand how the ocean came to be on it, and it interacts, of course, with the earth underneath it. We're going to start by talking about plate tectonics. Plate tectonics is one of those things that when they discovered it, it made everything else about geology makes sense. It's almost amazing that it took us so long to figure it out. Well, actually, it isn't that amazing. I'll tell you why. The guy who first came up with it was a man named Alfred Wegener, truly a genius. He was a meteorologist, not even a geologist, but he spent a lot of time alone in Greenland. I suspect that gave him a lot of time to think. He published a book about it. And you don't need to memorize all this stuff on here. I'll tell you what I want you to know about him. So what he did was he came up with this hypothesis based on data saying that the Earth was made up of these different plates and that they moved relative to each other. The evidence he used was basically shapes, fossils, and, well, instead of coal beds, put paleoclimate down there, because coal beds is just a part of paleoclimate. I'll fix that later. Anyway, the shapes I'm talking about are the continental shapes. Any school child who's looked at a globe can tell you that it looks like you could push, South America across the ocean and it would fit under Africa pretty nicely. India, Australia, and Antarctica kind of work the same way. They could all be pushed together. And they were at one time pushed together, although he was the first person to come up with this idea. The second line of evidence or data he had that gave him this idea was fossil distribution. If you look at these fossils, which are shown in bands of color, and then they show, what the animal or plant was that is in that band of color, you'll notice that these are, dinosaurish type animals, warm weather things, and pretty big too. They aren't the kind of thing that would swim across an ocean. Yet you can find this guy, I'm not even going to try and pronounce that name, in South America and Africa. Well, now how could he have gotten there? There's 2,000-3,000 miles of ocean in between there. Same with this guy, definitely not a swimmer. And you can find his bones or her bones in India, Antarctica, Madagascar, and Africa. The plant, okay, you can find that in all 6 places. Plants can blow the seeds, on the wind and across the ocean, but still, Antarctica is not actually, at this time, a very good place to find plants. And we have our sort of crocodilian type thing that we can find in both Africa and South America. So again, he says he believed that these continents were touching at one time, so that these animals and plants wouldn't have to go across oceans. They could just walk across. Now the coal beds, which again I told you to read as paleoclimate. Paleo means ancient and climate means climate. This is the map that Mr. Wegener came up with when he did. You can kind of see, hopefully, North and South America, Africa, Eurasia, Antarctica. I believe that's India in there. But what I really want you to pay attention to are these things that look like Band-Aids. Those are supposed to represent deposits of coal nowadays. Coal is created by long-term swamps where tens of thousands, over tens of thousands of years, tens of thousands of millions of tons of plants die, fall into the water, get piled up, compressed, and eventually lithified and turned into coal. But this can only happen in a swamp, and swamps are generally hot, humid places. The places where you find these coal bands nowadays are not hot and humid and tropical. By the way, this black line was what he believed, Mr. Wegener believed, would have been the equator back in the day that these were all pushed together. The other evidence of paleoclimate would have been evidence of ice sheets. So when you have an ice age and you have mountains of ice that are a mile or 2 thick that are moving across the land, we call those ice sheets. And there's evidence of ice sheets that cover Africa, India, South America, I believe, and Antarctica, that he believed were all one ice sheet at one time, which would have only made sense if they had been all pushed together. And also would have been very, very cold, right? And for example, Southern Africa is no longer considered a very, very cold place. So he believes that the continents were moving around. So the hypothesis was basically an educated guess based on data or observation. That's the definition of a hypothesis, right? It wasn't a theory yet. A theory is when it has lots and lots of evidence. Now, plate tectonics is a theory. But at the time, unfortunately, people didn't really believe him because he couldn't explain how the continents moved around. And this was before satellites, of course, and I don't even know when planes started moving around, but even in a plane, you can't see the continents moving. We can see it now with satellite data, but they don't move very fast. And to, your average person standing on the land, to tell them, yes, the planet is moving under your feet, it doesn't really seem very credible. Actually, here in Yuma, where I'm talking from, we are moving to the southwest approximately 2.5 inches a year. So not breaker speed. Actually, even for plate tectonics, we're moving pretty slow over here. But it's hard to imagine before satellites how anybody would have believed it at all. So nobody believed him. And then eventually, World War II and a man named Harry Hess came along. Harry Hess was a geologist. During World War II, he was in the Navy, and he worked in a submarine. He was in charge of the sonar. So he's running around in a submarine, supposedly looking for German submarines, but he was also a scientist, right? So he left the sonar on all the time instead of just when he was looking for submarines. And he eventually made a rough map of the Atlantic Ocean. So that's what we're looking at here. So here's America, here's South America, here's Africa, Spain. Over here's got to be the UK, Ireland. And what we've got here is a huge mountain chain that goes down the middle of the Atlantic Ocean. It actually wraps around most of the world, but this is what he was seeing back then. It's highest in the middle. It gets smaller as you get further away from it. It comes down into some plains, but we also have, some seamounts back here. We'll be talking about all these different topographic features of the ocean basin eventually, but, this is your first introduction to them. Near the land, it's more shallow. We call that the continental shelf, and then this would be the continental slope where it gets deeper. Anyway, this is what he found. And he came up with this thing called seafloor spreading, which would explain continental drift. And it basically works like this. There is magma coming up in the center of the ocean in that highest part of the mid-Atlantic ridge. He believes, and it is a very long, tens of thousands of miles, I believe, long volcanic chain. And magma comes up, and it comes up and it cools and it becomes igneous rock. And then more comes up and it pushes the rock that's up there already apart. So one side is going towards Europe and Asia, and the other side is going towards the Americas. So that would cause the seafloor to spread and the Atlantic Ocean to get bigger. The Atlantic Ocean is getting bigger, very slowly, probably only about 6 inches a year, so it doesn't really matter that much to anybody, but it is slowly getting bigger. And it can reverse, and it can turn around, and it can come back together. And we have evidence that it's done that 2 or 3 times. We call that, when oceans open and close, we call those Wilson cycles. So now you know that not only is the lithosphere broken up into plates, but these plates move relative to each other. But they can't just all spread apart. If they all spread it apart, right, our world would puff up like a piece of popcorn, right? They can't all spread apart. So we have 3 different types of plate motion. and 3 different types of what we call plate boundaries. The boundaries are these red lines that mark the boundaries between plates. So at these plate boundaries, you can be spreading apart. They're called spreading centers. They can be coming together at subduction zones, and they can be sliding past each other at transform zones. We will start, and they are also moving at different speeds. These arrows show you 2 things. They're vectors. They show you 2 things. One, they show you the direction that the plate's moving. So, for example, you can see that the Pacific plate, by the way, this is an oceanography class, so hopefully you do have at least looked up your major oceans. So you can see the Pacific plate is mostly moving west, and rather rapidly. When I say this is a vector and it gives you 2 pieces of information, that means the length of this line tells you how fast it's moving. So down here they're showing you, well, if the line is this long, it's moving 5 centimeters a year. And this is a little faster than this. Maybe it's moving 6 or 7 centimeters a year. And then earlier I told you that here in Yuma, which would be over in this area, right, that we're actually moving rather slowly, even for a tectonic plate. So that's our little vector line. We're only moving a couple centimeters a year. But you can see that these things are moving in all different directions. Over here, it's quite a mess. This mess is why they have so many earthquakes. Remember, you've got these big, huge masses of land, and in this case, they're coming at each other in many different directions. And even if they're moving very slowly, you've got a lot of land. So here is another picture of the plate boundaries, the major plate boundaries. You know, there are smaller ones that aren't shown here, and they're shown in blue. They're covered up mostly by little yellow dots. The little yellow dots are a year's worth of earthquakes on the planet. You'll notice that most of the yellow dots happen to be near plate boundaries. This is our area I was talking about earlier that has, you know, all the vectors going all different directions, right? They have a lot of earthquakes. And the little red triangles are volcanoes, because it's easier for lava to come to the surface when there's a crack in the plate, right? It's only logical. Notice we don't have a lot of either volcanoes or earthquakes in America except on the West Coast, because our only plate boundary is our famous San Andreas. Okay, so let's get down to the nitty-gritties of the different types of plate boundaries. 1, we've got the ones that spread apart. We call those divergent. 2, we've got the kind that come together. We call those convergent. 3, we've got ones that slide past each other. We call those transform. Let's start with the divergence. Okay, the mid-ocean spreading ridge, which I showed you, is a divergent plate boundary. It would work something like this. Now this is the lithosphere up here, and these arrows are showing you the mantle. We don't talk too much about the mantle, but essentially the mantle, which I'll explain a little bit more about later, is what makes the plates move. It's not quite solid, it's not quite liquid. Think of it as kind of a Play-Doh-like substance, but it's essentially rock. And if it comes to the surface, it becomes lava, magma. But it can move, not very fast, but it can move. And it's moving, and we believe that's what's making the plates on top of it move. I myself like to think of it as something like Jello, all right? Jello with the plates on top, and it's moving around. Now here it's showing that if this is the mid-ocean spreading ridge, and over here is Eurasia, and over here to the left is North and South America, that the mantle is moving like this. Oops, sorry. Moving to the right, dragging the eastern half of the mid-Atlantic plate to the right, and it's going like this and moving the other half towards North America and South America. And then the magma comes up, it solidifies, and then more comes up, and it pushes it to this way or to that way. So of course there's going to be a lot of earthquakes wherever you have a spreading ridge. Let's go back for a minute. They probably don't measure earthquakes much in the center of the ocean. Let's look. Oh, they do. They measure some of them anyway. At least this is where because we keep track. The United States Geologic Society measures earthquakes all over the United States. But yeah, it's not real surprising that there is a lot on those spreading ridges. Okay, so that's divergent. It's moving apart. These are all the places on the Earth, well, the major places on the Earth, where there's a divergent plate boundary. Notice most of them are in the ocean, and this is the famous Mid-Atlantic spreading ridge, but it like I said, it wraps around the whole planet. So, and it's mostly underwater. It comes up through the Baja, right? The Baja is actually spreading out. And some people sometimes ask me, is the Baja ever going to be an island? Well, yes, in geologic time it will. But now that you know a little bit about how fast plate motion is, it's not going to happen in our lifetimes. I don't even know if it'll happen in our species' lifetime. But it is basically slowly being created into an island. It disappears here. That's where the San Andreas is. So the San Andreas is not a spreading ridge, but it comes out over here. We'll have to find out what the San Andreas is. Okay, a convergent plate boundary, where the plates come together. This actually does create quite a lot of volcanoes, and a lot of, this is the one that creates the most volcanoes, and it does do an awful lot of earthquakes too. So they're coming together. The example I use most is the Pacific Ocean. I think it's the Nazca Plate is diving underneath South America. I think it's the South American plate. So it's diving underneath. Now, so here, that over here on the left, that's the picture from above. Now, if we were looking at it in the side, if we could take a cut out of the ocean, yeah, it's the Nazca Plate. We got the ocean here. The Nazca Plate is coming towards the South American Plate, which is coming towards the Nazca Plate. What's going to happen? You got these two behemoths coming at each other. Well, one of them's going to have to give. One of them's going to have to, what we call subduct. Subduct means go underneath. And the one that subducts is generally the heavier one, the denser one. So the Nazca Plate is denser than the South American Plate, so it subducts underneath it. At the very end of this lecture, I'm going to tell you why some crust is more dense than other crust, but we'll get to that later. So anyway, the Nazca Plate is heavier. It subducts. It says earthquake zone, right? Because you got these one oceanic crust sliding underneath South America. That's going to do a lot of rubbing and cause a lot of vibration, right? So you're going to get earthquakes. Then it goes down further and further, and as you go deeper into the earth, it gets hotter and hotter. It's called the geothermal gradient. And then when you get to a certain point, when it starts to melt, the constituents that are less dense, right? Because remember, this Nazca Plate's got a lot of water-soaked sediments. You get down there, and that water-soaked sediment, a lot of that is relatively light compared to the other things that are down there. And so they want to bubble back to the surface because they're less dense, right? They're like the fat on a stew. They want to bubble up to the surface. It's not natural for them to be down there. And so when they bubble up, what you end up getting is volcanoes and mountain ranges. Now, where a plate subducts, we call those trenches. The trenches are the deepest part of the ocean. They're up to 6 miles deep, subduction trench. And about 50, 60 miles inland away from the trench is about where you tend to get the volcanoes. So we go back to this picture on the inset, the left-hand side here. You know, they're showing you this gray line with the triangles. That would be the trench. And then that's Chile. Oh, right about here. Oh, there's a few mountains, or a few volcanoes they're showing you. This is about 50, 60 miles from that. We've got our Andes Mountains. The Andes Mountains line the west side of South America because of the subduction of the plates going on underneath. And the mantle underneath, what it's doing here, instead of spreading apart, they're coming towards each other, and it's dragging the crust towards each other. So that's our convergence. Transform. Now here's our San Andreas. Transforms are a little bit more complicated. They're kind of where you know, these pictures they're showing you, they look so neat, but number one, the world's not that neat. And number two, the world is a sphere. It's not actually flat. So even with the spreading ridge, the mid-Atlantic spreading ridge, like they're showing you down here at the bottom, if I have a chance, I'll have to show you this on Google Earth, but because Google Earth shows you the mountains, the bathymetry of the Atlantic Ocean, and you can see the transform faults pretty nicely there. Anyway, so this is kind of a line where the mid-ocean spreading ridge is. Well, the thing is, you know, it's trying to spread one to one side, one to the other, but again, this is a ball, okay? It's going to have to spread further in the middle where the Earth is fattest, and not so far as you get further away towards the poles. Well, how does that work? What you end up having is sideways motion underneath. Where, see here, this would be the mid-ocean spreading ridge. Hang on, let me see if I can get rid of that. No, I can't. Okay, that would be the mid-ocean spreading ridge. This is the mid-ocean spreading ridge. So is this. But why aren't they lined up? Well, it just didn't work, right? Like I said, curvature of the Earth. So they ended up breaking and sliding. And so this circled thing here is the slide. And that's called a transform fault. Let me see. I would like to show you that, and I want to see if I can do it, and will it still record? Oh, it says continue recording. Good. Oh, they gave me one and didn't. Oh, there it is. Good. Good, good, good. All right, close. All right, Google Earth. Ta-da! Now, I don't know if you can see it, but see this kind of broken sort of thing that goes, you have to kind of look at it carefully. But there is a line that goes around the planet. That's the mid-ocean spreading ridge. And, oh, here's a perfect spot, right? Look at all these sideways cracks. Those sideways cracks are the fractures, the transform faults that I'm talking about, right? Because it just can't make a straight line because it's doing it on a ball. All right, let's hope that it's still. I'm almost afraid. I'm almost afraid that it'll cut my presentation off and I'll have to do it all over again. That would be a pain. Okay, I'm going to assume that it is not doing that, but I do want to get back into presenter mode. And I guess I'll just hope that it is still recording. All right, so here's San Andreas. Like I said, there was a spreading ridge coming up the Baja, and it continues north of California, but when it goes under the continental United States, it turns into a transform where it's sliding. And this part of the country, this plate is moving that way to the southeast, and this part is moving to the northwest. Notice we have lots of cities right on top of the fault. We're a little short-sighted that way. Anyway, that fault is always going to be there. It's always going to be moving as long as there's going to be humans on this planet. So that's always going to be a problem. And they're not even moving at the same speed. So you can just imagine, of course, there's always going to be earthquakes there. When will there be the big one? Anyone's guess is as good as anyone else's. They can, figure it out statistically that there's this much chance happening in 50 years or whatever, but people aren't really good with statistics, most people. That's why the lottery is so popular. All right, so plate tectonics explained so much about geology, right? And oceanography in particular, because this was about the time people were arguing, is the Earth only 4,000 years old, or is it really, really old, like 4 billion years old? And one of the things they're saying is, well, the people who said it was not that old were saying, well, it's if it's that old, how come the sediments aren't thicker in the ocean? Why aren't they thicker? Do you know? Can you figure it out? Think convergent plate boundary, where they're being subducted. Mother Nature recycles the crust, okay? So, it collects it's brand new rock right in the mid-ocean spreading ridge, and then as it moves away and it's collecting sediments on top of it, by the time it has its thickest amount, it subducts and gets melted and starts over again as magma. It explained how the continents moved. Yay! And it also explained the fact that they couldn't find any seafloor fossils that were older than 180 million years. And again, they were arguing about, is the Earth really old or is it really young? Well, if it's really old, can't be that old because the fossils aren't that old. Well, again, they get subducted. This is just nice. I don't know if I can, let me see. It sometimes takes me a second to pull it up. No, that's not what I wanted. Hang on. I wanted to show you this. This is what we call a lava lake. Where is it? It's in East Africa. I know that. It's at a spreading ridge. A new spreading ridge, because most spreading ridges are in the ocean. This one's on the land right now. It'll become an ocean someday, but right now it's on the land. And we have things in there called lava lakes. And this lava lake, where the lava's bubbling up, let me kind of get past the commercials here, if I can, skip ad. We'll show you, look at those, you see the black parts? That's the cooled lava. That's kind of like plate boundaries. And you can see they're spreading apart in some places. They're coming together in other places. And they're sliding by each other in other places. So this is kind of like a miniature, sped up version of what's happening on the surface of our planet. Except we got oceans and continents on top of these plates. Cool, hey? Like I said, it's a really crazy cool world we live in. It really is. All right, I hope I'm still recording. Let's put it back in presentation mode. Switch, display settings. I seem to still be recording, I think. I hope. Phanerozoic plate tectonics animation. All right, now this I can show you. Oops, wrong one. No, that's the wrong one. That's the right one. Okay. This shows you a retired professor's reconstruction of the last 540 million years on our planet. So we'll start with the Permian. He worked at the University of Chicago. So he puts a little red dot there to show you where he is, right? So this is what it looked like, Christopher Scotes. 540 million years ago, right? To the present. Hopefully it doesn't have any weird music. It used to. Okay. So they're able to figure out, you know, where the continents were and how they moved. It's not my specialty, so I couldn't answer that. How that happens. They've showed you, you know, they got some of the drawings in here so we can recognize our old places, right? The little red dot is over there by the Great Lakes. They're trying to show you some different countries. The dark blue is the deep ocean. The light blue is shallow ocean. That white blob down there on the bottom, that's an ice age that's happening, and it's showing you the extent of the ice. Cold, cold, cold. The brown is either deserts or mountains, or both. Especially depending on how much ice we have on our planet, the oceans rise and fall. When we have more ice, the water is in the ice, so the oceans go down. When we have less ice, like back when the dinosaurs were around, the oceans are high. Notice that, well, don't have time to notice these things. There goes India. It's crash landing into Eurasia, creating the Himalayas over there. Hopefully you noticed the part where all the continents were together. You can always watch that yourself again. It's really kind of cool. Show it to a younger brother and sister. They might appreciate it, hopefully. Where's my presentation mode again? Okay, but what is driving plate tectonics? That will be part 2.